Good morning, everyone. Today's webinar title is Transformer Differential Protection, Challenges and Solutions. Before proceeding to the webinar, I will talk about the scope and what do we have for the future scope with this webinar. So in this webinar, I will be talking about Transformer Differential Protection Scheme in particular, especially for a two-winding transformer. We will talk about single phase and the three-phase differential protection scheme. What are the basic principles behind that? And then we will jump on to the challenges faced by relay designers or relay settings engineers in order to have an effective transformer differential scheme. And then some of the methods adopted by relay manufacturers to address those challenges. For future scope, we will take care of the performance of the schemes discussed. We will also talk about the assessment of methods adopted by relay manufacturers, and then also about some of the testing methods for testing transformer differential schemes. We will just cover the pickup test, timing test, slope test, two-fault test, all those kind of tests, and what kind of instruments you need to test them. This is kept for the future. So let's start with the outline of this webinar. I will start with the introduction, where I will explain single-phase differential basic principle, and then I will talk about three-phase basic differential, and then we will just talk about like a functional overview of transformer protection schemes, electrically and mechanically, how you can protect a transformer. And then we will jump on to very specific electrical protection scheme, which is phase differential. We will start with the operation principle of single phase, and then with the three phase. And then we will talk about challenges to differential. What are some of the challenges faced by relay designers and relay manufacturers in addressing transformer differential? And then some of the methods adopted by relay manufacturers to address the challenges which are faced by people out there in the field. And at the very end, I would talk about conclusion. I would conclude my presentation with a few notes, and then we will just talk about like a very basic of how you can test differential. So let's start with the introduction. What is a power transformer? IEEE C57.12.8, IEEE standard for protecting power transformers, it states that a transformer that transfers electrical energy in any part of the circuit between the generator and the distribution primary circuits is termed as a power transformer. So if you talk about the components of power transformer, these are few of the components, kind of major components in a power transformer. Bushings, so high voltage bushing, you have low voltage bushing. This example right now, this image is specifically for a two-winding transformer. You have windings. You have low voltage winding, you have high voltage windings. Then you have core. A transformer also have radiators or the cooling tubes. Then it has a tank, also has a mechanical device which is called as tap changer, and then insulation between the windings and the bushings. So these are few of the transformer components which basically form a transformer. Now, out of all these components, the component which fail the most is winding. Now, I've gathered this data from C37.91 standard, which is specifically for United States. It states that 37% of all the transformer failures in the year between 1983 and 88 were due to some winding failures. Now, this winding failures can be caused by overheating of the windings, can be caused by vibration effects, can be caused by insulation deterioration. So these could be some of the causes for winding problems. Now 26% um, issues for the transformer failure were due to some miscellaneous. And under this miscellaneous falls problems due to CTs, oil contamination in the transformer, you have oil leakage issues in the transformer. So these kind of problems fall under the miscellaneous category. And then you have 22%, which is also a big chunk of the total failures, which is due to tap changers. Tap changers are basically mechanical devices, and due to mechanical devices, they have motor in them. And those motors may have frictional effects, frictional issues, which could lead to failures in the transformers. So why do we need to protect a transformer? So a transformer, there is high cost of repair and replacement involved. Everyone is aware that transformer is an expensive piece of equipment. And if you're taking a transformer out of service, it might require you to spend a little time on transformer for maintaining that, or for having the repair to be done, which could cost too much for a utility. We also can minimize the risk of damage to adjacent equipment if we design an effective protection scheme. We can also limit the damage to the faulted equipment if we are taking out the transformer as soon as we can. We can also minimize the possibility of fire, which might cause if you don't have a good protection scheme, because there is oil involved, there are windings in the transformer, which could lead to fire hazards. And also to improve personal safety. And last but not the least is to avoid unnecessary cascade tripping. So if you have a good protection scheme, you can avoid backup protection schemes to be coming into picture to not have cascade tripping. So these are some of the points for why do we need protection. Now let's talk about how do we protect a transformer. So there are two ways you can protect a transformer. One is from the electrical standpoint, and then the other one from the mechanical standpoint. For electrical standpoint, we have various schemes involved which address different fault conditions in the transformer. And these are differential, and the ANSI code for differential is 87T. You have overcurrent protection, which acts as a backup to differential a lot of times. Then volts per hertz. So this is basically an abnormal condition, which is overfluxing of the transformer. You have overfrequency, underfrequency elements to address the issues in the frequency if it is going beyond a set value. From the mechanical standpoint, a transformer has a Buchholz relay, sudden pressure relief valves, and thermal overload elements. So these mechanical protection address the issues caused due to gas accumulation or oil or some problem with the oil in the transformer. So this webinar will specifically talk about differential. So let's jump directly to the differential now. So in this example, I've taken a single phase transformer, and it's a two winding transformer. I have CT1 on the primary side, CT2 on the secondary side. So the whole idea of differential lies with the Kirchhoff's current law. So what does Kirchhoff's current law states? So Kirchhoff's current law states that at any given node in the power system network, the amount of current entering is equal to the amount of current leaving. So now let's apply this law here in this example. So if we apply the Kirchhoff's current law at node A, what I'm going to see. So let's see, let's have the primary current flowing in CT1 and CT2 in this direction. And according to the CT polarity, the current entering the relay would be in this direction. So according to Kirchhoff's current law at state A, at node A, my current entering would be equal to my current leaving. If I have both the CTs exactly same and the ratios are also compensated, then I would see no current flowing through my operate winding. But as you all are aware, that no two CTs can be similar. So for addressing this particular issue for this kind of a scheme, researchers came up with the idea of restrained differential. So now let's talk about what restrained differential is. So this restrained differential will have restrained windings, and it will not lead for an operation of the relay for external faults or for any abnormal condition. So the idea of differential is if I have an external fault here, and if I have my source on the CT1 side, the primary currents flowing through both the CTs will be in this direction, assuming I do not have a source on the CT2 side. And the secondary current would be in this direction. Now, if I have everything ideal, I'm assuming ideal conditions, I would see no current flowing through my operate winding. But that's not the case. As I said, there would be two CTs which are different. We would always face problems with the CTs. So no current in operating coil for external faults, ideally. Now let's take an example of an fault which is happening between both CTs. Let's assume it's a single phase to ground fault. And in this example, let's say I have connected my source, it's on the CT1 side, and also there is a source on the CT2 side. Primary current flowing through the CTs would be in this direction, and then secondary current flowing according to the CT polarity would be in this direction. Now, if you remember, we talked about Kirchhoff's current law. So if you apply Kirchhoff's current law at node A, these currents flowing through the restrained windings will add up and it will flow through the operate winding. And if a current flows through the operate winding and if it's above a set value, it's going to trip the relay. So from these two examples, what I did was I'm designing the differential scheme. And this differential scheme only works when there is an internal fault. When I say internal fault, I mean that the fault is between the CT1 and CT2, which I say as in zone. So for any in zone faults, I have to operate my relay. And for any out of zone faults, I should not operate my differential relay. That's the whole idea behind differential. So for restrained differential, if my operating current is above K times my total restrained current, then I would declare an operate condition and my differential relay will trip. Now we will discuss this K factor in my further slides. Now let's see an example of a three-phase differential. I have here a delta Y transformer with CTs on the delta side connected in Y fashion, and CTs on the Y side are connected in delta fashion. And let's see a fault happening on A phase and assume it's an A phase to ground fault. Now, with this structure, with this winding configuration, there would be flow of current in this direction. So a three-phase differential will have differential elements on each phase, and it will give you a clear picture of on which phase the differential current was higher than normal, and it would declare whether it was an A phase differential or a B phase or a C phase. Now, this differential scheme is used, it's very popular among the whole industry, and it's used as a primary protection for protecting transformers. There are reasons for differential being the primary protection, and I have listed down a few reasons here. Differential protection is sensitive. By sensitive, I mean it operates for low level values of operating current. It clearly differentiates in zone and out zone faults. It operates as intended if designed properly. What it means is it will operate only for in zone faults. So it will operate only for in zone faults, which exactly it is intended to do. And this will only happen if it is designed effectively. Then you have security. If you design the differential scheme in an effective way, it will not operate incorrectly. What it means is if I have an external fault in the system, I would not operate my differential for that external fault. So it does not operate incorrectly. That's what security means. And the last but not the least is speed. Differential protections are usually kept for no delay. They operate as fast as they go. So now we talked about phase differential operation principle. It's being used as a popular scheme out in the industry. But there are a few challenges to differential, and this whole webinar will be talking about those challenges. What are some of the challenges? The scheme looks simple in theory, but what are some of the challenges that are there present? So I've listed down a few challenges here. Current mismatch caused by CTs, different CT ratios, phase shift due to winding configuration, zero sequence current, errors due to tap changes. So I'm going to talk about each one of the challenge one by one, and then after that, I will discuss what are some of the methods adopted by relay designers to address each challenge. So let's start with current mismatch caused by CTs. Again, here I've taken an example of single phase transformer with single phase differential relay. So single phase differential relay is in the picture. I have secondary currents flowing in this direction as of now. So in an electromechanical differential relay, there are something called as current transformer ratio matching taps. So what are these taps? So these taps are nothing but the value of secondary current entering the relay. And based on these tap values, the pickup of a differential relay is defined. So in this example, the relay has a pickup of 0.3 times tap, and the taps are 5 for winding one side and 5 for winding two side. So 0.3 times 5 would give me 1.5 amps. That is the value of my pickup. Now, what is the problem with this kind of a relay? So as you can see, the taps are not in a discrete way. They are fixed. So I only have 2.9, 3.2 till 8.7, and we'll see a problem if you have your tap value coming out to be somewhere not in these values. So let's take an example, what I'm trying to say. So let's assume we have a 50 MVA transformer, 110 volts on the high side, 110 kV on the high side, 33 kV on the low side. So if you compute the primary current, it comes out to be 454.54, and the secondary of the transformer will see a primary current of 15.15 amps. And if in this way the CT ratios are selected as 500 to 5 and 1600 to 5, I would get winding one current as 4.545 and winding 2 current as 4.735. Now the problem is I do not have a tap which says 4.545. Neither do I have a tap which says 4.735. What I have is a tap which is 4.6 or 5. So what I will do, I will take out the screw here from 5 amp tap and put it on 4.6. And I will do that for both the windings. If I do that, I would get a mismatch of 4.13%, and this mismatch is between the currents of winding 1 and winding 2. And this mismatch can lead to a value of operating current higher than the set and could lead to differential being operated. So how do we address this problem? For electromechanical relays, it is advisable that you select the most appropriate CT ratio and the most appropriate taps. For microprocessor relays, what they do is they do some internal math to eliminate these kind of errors. So they utilize these kind of equations and they compute the tap value to the highest possible decimal. And with the highest possible decimal, you would not have any issues of mismatch. You would see a 0% mismatch. So some relays, some microprocessor relays, what they will require is they will require the setting of MVA of the transformer, high side and low side voltage of the transformer, CT ratios, and what are the connection types of the transformer. And based on that, they would compute the tap value for both winding 1 and winding 2 if you have a 2-winding transformer. Some other relays, what they do is they use the voltage values on the high side and the low side, and then they compensate that for the secondary side. So they define CT ratio for primary side, and based on the CT ratio on the primary side, they adjust the secondary side CT ratio. So different manufacturers utilize different ideas. The second challenge is phase shift. So phase shifts will happen whenever you have a delta winding on one side of the transformer and a Y winding on the other side of the transformer. So I've taken an example here which has a DAB on the high side for the transformer and Y on the low side. And my CTs are connected in this fashion. I have CTs Y connected on both the sides. So the problem with phase shift is what will happen is I have a delta connected winding and I have a Y connected winding on the transformers. And if you see some math, it will tell you that there is a 30-degree phase shift between the currents entering the relay on the winding 1 side and winding 2 side. And this 30-degree effect can produce a difference in the currents, which could lead to the operation of differential. I also see that there is a √3 factor coming into picture. Many of the microprocessor relays, what they do is they eliminate this √3 factor by the CT mismatch error that we discussed before. But different transformer windings have different kind of configuration. You would see not only 30 degrees, but you can face the phase difference between primary and secondary anywhere from 30 to 330, depending on how your transformer is, whether it's a YD7 type, whether it's a DY1 type, DY5 type, based on how the transformer winding is configured, you can have the phase difference from 30 degree to any multiple of 30 degree till 330. So how do we address this issue? Electromechanical relays, they use a concept of external compensation. By external, it means that electromechanical relays will always require change in the CT winding configuration. So what I'm trying to say here is if I have a delta Y transformer, I would connect my CTs on the delta side as Y, and on the Y side of the transformer, I would connect my CT to be delta. Now this delta effect on CTs and winding transformers and transformer winding will have 30-degree effect coming into the relay on winding one side. Similarly, the winding two side will see a 30-degree effect. And this 30-degree effect on both sides will compensate for each other, and there would be no current on the operate winding if everything is ideal. So that's how you would compensate for the phase shifts in electromechanical relays. That's the only way in electromechanical relays. But for microprocessor, there are two methods. First method is you correct the CT windings. The second method is if you don't want to correct the CT windings, that's fine with microprocessor relays. What they do is they do some math inside the relay to address this issue, which is called as internal compensation. What they do is they define some compensation matrix involved with different winding configuration, and they basically compensate the angles which is coming out to be different for both the windings. So let's take an example to have a better understanding of what I'm trying to say. In this example, I've taken a transformer DY1 with delta on the HV side, and my CTs are Y and delta respectively for high voltage and low voltage side. So let's start with the currents coming out of the transformer winding. So this is a single phase current, A phase current vector without for the coming outside the transformer winding. So you can see that I have a phase shift created due to the delta Y transformer type. Now, if I have CTs which are Y and delta connected for high voltage and low voltage side respectively, I would have these vectors. So this black vector is basically representing the winding one current which is entering the relay and winding two current entering the relay. So you can clearly see there is no phase difference between both the winding currents which are entering the relay. So it has been taken care already by CT winding. So there is no compensation requirement by the relay to address this issue. Now let's take another example where the relay has to compensate internally. So I have taken YD7 transformer configuration and delta is on the low side. So let's start again with the currents coming out of transformer first and then coming out of the CT. With the transformer, I will have my single phase A phase current to be in this, to be of this vector diagram. After the CTs, if I have CTs Y connected on both sides for this example, I would have my winding one current and winding two current in this fashion. It's clearly observable that there is a phase difference between winding one current entering the relay and winding two current entering the relay. So there is a 210-degree phase difference, which has to be compensated internally by the relay so that there is no difference in currents flowing through the operate coil and which might cause a differential trip. So 210-degree counterclockwise compensation is required by the relay in this particular example. Now, what do different microprocessor manufacturers do? Some manufacturers, they just give windings, they use compensation matrices, and they give each winding any number between 0 to 12. which basically corresponds to number of 30-degree angle increments to be rotated. So they give winding 1 a specific number for CTs and winding 2 a specific number for CTs. And then based on those numbers, they basically eliminate the problems caused by phase difference. These numbers are to be set by the user. Some manufacturers they define compensation matrices for both transformer and CT separately. So there are different methods adopted by the relay designer and manufacturer to address this phase shift issue. The third challenge would be something called as zero sequence currents. So what are basically zero sequence currents? These are the currents which are created in the power system whenever there is an unbalanced fault. So I've taken an example of an unbalanced fault vector, and according to the Fortescue's theorem, what it states that any unbalanced vector can be resolved into 3 balanced vectors: positive sequence, negative sequence, and zero sequence, in order to have better understanding of what the fault is. So we'll not go in detail into the symmetrical component theory. I just want to focus on zero sequence currents. The property of zero sequence current is it's only present during ground faults. So if you have a single line to line to ground, or a 3-phase to ground fault, you would definitely have zero sequence currents flowing through the system. The second property is it gets trapped in delta winding as circulating current. So with these two properties, we will see how it can create problems for differential scheme. So let's take this example. I have a delta transformer, delta Y transformer, and on the delta side, I have CTs Y connected. On the Y side, CTs are again Y connected. If you have an external fault, and I'm assuming it's a ground fault, single line to ground fault on A phase, this is how you would see the flow of zero sequence currents. You would only experience zero sequence currents flowing on the secondary side of the transformer. On the primary side, there would be no flow, because if you remember, I talked about zero sequence currents only flow when there is a ground fault. And the second property was it gets trapped in a delta winding. So the primary side has a delta winding, which will not produce the zero sequence currents on the line side. So you would the relay on the winding, the relay will not see zero sequence currents on the primary side, but it will see on the secondary side. So there is difference in the currents on both sides, which could create an operating current to go beyond a value and can cause differential to misfunction. So how do you eliminate this zero sequence current to have to not have any maloperation from differential? The simplest way to eliminate zero sequence current is to have Y connected CTs on the side of delta connected winding and vice versa. So this would eliminate the zero sequence currents entering the relay in numerical way, and there would be no zero sequence currents going through the operating coil. In microprocessor relays, this is done by compensation matrices, which I talked about earlier when we talked about the phase shift issues. So we'll see an example, and we will see this how a microprocessor relay addresses the issue of zero sequence elimination. So this is a classic example of one of the metrics. So this is CTC1. This matrix basically is nothing but a delta connection. So you can clearly see there is a presence of zero sequence current, but it's numerically removed by the relay So microprocessor relays, they numerically remove zero sequence by the use of compensation matrices. Even though if you do not have CT windings the way you want, you can remove them numerically by using these compensation matrices. The next challenge is with the tap changes. So what are tap changes? Tap changer is a mechanism in transformers that allows for variable turn ratios to be selected in discrete steps. So what will happen if the relay engineer is not aware of a change in the tap by a substation engineer? As you can see, I've taken an example here. This is a transformer, I think it's Waukesha, and the nominal value of voltages for this transformer is 12.47 kV, and it can go to a max of 13.716 kV. And corresponding to those two values, I have 1389 amps and 1263 amps. So if there is a change in the tap and which is not been seen by the relay designer, if he is assuming the current will always remain to be 1389, we can have a maximum error of plus minus 10%. And if it's a no-load tap changer, maximum mismatch can have plus minus 5% of error. So how do we address this issue? So relay designers utilize the concept of percentage restraint to address this problem. So what they do is they provide additional slope in slope characteristic to provide a margin for such errors. We will discuss in detail what this slope characteristic is in my next slide. But just to give you an idea how the issue of tap changer is being addressed by the relay designers. The next challenge, which is one of the most important challenges faced by the protection people, is CT saturation. So what happens when a CT saturates? When a CT saturation occurs, the ratio error increases and the secondary current is no more linear to the primary current. So if the secondary current is not linear with the primary current, you will not have the exact ratios. And because of that, there would be some mismatch in the currents flowing on the winding 1 side and the winding 2 side, which would result in the misoperation of differential. Why this is misoperation? As I said, CT saturation is not a condition of internal fault, and my differential is designed to operate only for internal faults. So there could be two different types of CT saturation. One happens when there is high symmetrical fault, and it will only have AC components in the waveforms and has odd harmonics. The other, which is a severe case, is caused by DC component happening inside the current waveforms. This DC component comes into picture when you have asymmetrical faults, or if you synchronize generator, your CT might saturate. And this is an example I've taken from C37 standard, which shows the waveforms of CT secondary. You can clearly see the distortion in the CT secondary waveforms. And this distortion, if you take the RMS of the current value, this could be different from coming from both the CTs and can result in differential to operate. Now, when I talked about tap changer, I said that I will cover later in detail what exactly are percentage restrained characteristics. So we discussed all the challenges so far. So far, we have discussed current mismatch caused by TPs, We discussed phase shift issues, zero sequence issues. We also discussed gap changer problems, CT accuracies. So what relay manufacturers do is they provide something called as percentage restrained characteristic. What it's plotted against restrained current on the x-axis and operating current on the y-axis. So if my operating current goes beyond the slope, then only I would say to my relay, hey relay, this is a condition to operate and you are supposed to operate. If it is lower than the slope, then I would restrain my relay from operation. As simple as that. So with this slope, I am providing all the margins caused by CT accuracy issues on both sides, by my tap changer issues, by magnetizing current errors, by the errors caused by my relays. And according to the standard C37.91, it is recommended to have the slope 1, which is on the region 2, to be somewhere close to 30 to 35%, which is just a recommended number. It can vary depending on your system and your transformer and also the CTs. So this percentage restraint characteristics takes care of all the challenges we have discussed so far. It also takes care of if you have a dual slope characteristic. So this region 3, it basically addresses the issues caused by CT saturation, especially on the external faults. So if you are having an external fault, asymmetrical or symmetrical, and if it's causing the CTs to saturate, this might create a differential current and can trip. So by providing this additional slope, I'm giving some margin to not operate, because external faults are not internal faults and my differential is not supposed to trip for that. So with this kind of scheme, I'm basically improving my dependability and security of the inverter. This is an example where it says the share of different challenges in the slope. Now let's talk about a few abnormal conditions which are due to transformers or due to system conditions which could come into picture and which could misoperate the differential. The first, the first condition is something called as magnetizing inrush. So what exactly is magnetizing inrush? So inrush is a high magnetizing current drawn by a transformer from the source. So whenever you are energizing the transformer, since the transformer acts as an inductor, it would draw heavy current from the source for its core. And this heavy current will be having only on the primary side, on the magnetizing circuit of the transformer, and not on the secondary side, which could lead to differential misoperation. This inrush can be caused in these three conditions. So the first condition is when you're trying to energize the transformer after complete de-energization. What it means is when you have demagnetized your core completely and then you're trying to energize the transformer, there is a possibility that the inrush could be there. The second condition is post-fault voltage recovery. So your fault happens, your voltage dips to a value, and then when you energize that, then it could cause a heavy inrush. The third condition is when you're trying to energize a parallel transformer, and because of that, since two or more transformers are connected parallelly, the other transformers will see some current flowing into them, and the test transformer can have the inrush. Now, this example here, this diagram I've taken especially for the case of when you're energizing the transformer after complete de-energization. So in this particular example, I have energized the transformer at the zero crossing of the voltage applied waveform. And according to the Lenz's law, it clearly states that my voltage should be in quadrature with my flux. So my flux would lie somewhere in the negative cycle, since I've energized my transformer on the zero crossing. But this flux cannot be negative because I stated that we have completely demagnetized the core. So according in theory, there should be no residual flux, but there would be some minimal residual flux, not in the negative cycle. It depends. And in order for this would not be there, and what it will do is, according to a Jamie, you there?
Yeah.
Okay, so I have to repeat this slide again.
Okay.
Okay. So now let's talk about some of the abnormal conditions in the system, which could be caused due to transformer or maybe some system conditions. So the first abnormal condition is magnetizing inrush. What is inrush? Inrush is high magnetizing current drawn by a transformer from the source. So since a transformer acts as an inductor when you energize it, it will draw heavy current from the source to energize the core. And this inrush can happen in primarily three different scenarios. First one is energizing the transformer after complete de-energization. What it means is when you're trying to close the breaker, and this time the transformer is completely demagnetized, you would experience some inrush coming into the transformer. The second scenario is post-fault voltage recovery. The name it clearly says when a fault happens and the voltage dips to a lower value, and when it's trying to recover, and that time you energize the transformer, then you will see inrush. Third scenario is energization of a parallel transformer. So if a parallel transformer is energized, even though the transformer under test is not energized, you would experience, this test transformer would experience current coming from that parallel transformer, and it could have inrush. So these three scenarios can cause inrush in the transformer primary winding. Now I've taken in this picture below, I will be talking about a case where I have energized a transformer after complete de-energization. So by complete de-energization or complete demagnetizing the core, it means that I have reduced the residual flux to a minimum value. And let's assume I'm closing my breaker at the zero crossing of the voltage applied. So Lenz's law states that the voltage is in quadrature with the flux. So with this law, in theory, we will see that my voltage will be in 90-degree shift with my flux. And if you remember, I said that the breaker is closed at the zero crossing of the voltage. So this would tell in theory that my flux should be on the negative maximum. which cannot happen because I've said that I've completely de-energized the core. So what the transformer will do is it will compensate for this negative effect, and it will change the flux shape, waveform shape to this shape. It will compensate the flux for the cycle, for the whole voltage cycle. And it can raise above the maximum flux to any value 2 times or more than even more than that, depending upon how much the residual flux was in the system, how you have energized the transformer, whether was it at zero crossing. There are many factors involved which can cause this high flux coming into picture. And in order to generate this high flux, the transformer will pull more current from the source. So this more current, and again, transformer core, just to let you know, transformer core saturates at any value higher than the maximum flux, which is phi m. And 2 phi m, it's more than that, so it would saturate the core. Now let's see what effect this high inrush will have on differential. So usually it's of the order of 10 pu, but again, as I said, it depends on various factors. What is the magnitude of inrush and the duration? These factors could be point on wave switching, residual flux, transformer type, size of the transformer, how far is the source, what is the source impedance. These are some of the factors which could affect the magnitude and the duration of magnetizing inrush current. So I was talking that there would be inrush, and with this inrush current, it would be only seen by the CTs connected on the primary side, not on the secondary side. So if CTs on the primary side sees that high inrush, and the CTs on the secondary side does not see that, again, the relay will see a difference in current, which could lead to differential being operated. But is this an internal fault? No, it is not an internal fault. It is just a property of a transformer. So how would I address this magnetizing inrush problem? The first method is even harmonic blocking method. So a lot of researchers and power system analysts, they worked on checking the waveforms of current, secondary current, during the inrush condition. And what they found was that this inrush current is rich in even harmonics, especially second and fourth harmonics. So utilizing this concept, relay designers, what they did was they came up with the concept of harmonic restraint. What it means is they set a value. Let's say I've taken an example here, just an example, 15 to 20%. If my second harmonic current goes beyond 15 or 20% of the fundamental current, then I would declare, hey, I have a magnetizing inrush condition and I would restrain my relay from operation. Some relay designers, they said that if we include fourth harmonics in this logic, I would increase the security of the relay. So they take the root mean square of second harmonic current and fourth harmonic current, and then they compare it against the fundamental component of the current. And if it goes beyond that 15 to 20% setting, then they just declare, hey, 87 element, you have to block. Electromechanical relays, they don't have this luxury of programming and math to be implemented. What they have is they have filter circuits. They have low pass filters which detect second harmonics, and if it goes beyond the number, you can declare they have a restraint element which gets operated and which just blocks the 87 to operate. Microprocessor relays, as I mentioned, they use these equations and they look for these conditions before issuing a percentage restraint differential trip in their logic. Some modern transformers which have good cores, good steel core properties, they sometimes do not experience the typical 15 to 20% of second harmonic during the inrush conditions. So on those cases, what they see is only one phase sees a value higher than 15%, but the other phases, they are well below that. So how to take care of those kind of problems? Because if you say that, hey, if I have my second harmonic content going beyond that 15 to 20% of the fundamental current, I would declare a restraint. But in this particular example, the relay will be restrained only on one phase, but the other phases will operate for differential. So what some of the relay designers do is they employ a concept of cross-phase blocking. So what this cross-phase blocking does is, in their logic is, whenever it sees the second harmonic current going beyond the set value, it blocks all the three phases. So if I experience magnetizing inrush or the second harmonic current over the fundamental current higher than 15%, which I'm considering right now as a set value, I would declare block for all the three phases, even if it's present in one phase. The other idea to address these kind of issues is something called as cross-phase averaging. So in cross-phase averaging, what some of the relay designers do is they just average the second harmonic component for all the three phases and then compare it against the fundamental. That is basically their setting. So it's not just second harmonic for one phase. You just average for all the three phases and then compare it against fundamental. If it goes beyond the set number, it will declare as restrained. The second abnormal condition, which is quite popular, is over-excitation. What exactly it is? It is nothing but overfluxing in the transformer. What by overfluxing it means excessive volts per hertz. So if volts per hertz on the secondary side is going greater than 1.05, according to that ANSI C37 standard, on full load conditions, then there is a condition of overexcitation. What are some of the reasons of overexcitation happening? So if there is a sudden loss in your network, then it might increase the voltage. And if it goes beyond this 1.05 factor, then the overexcitation condition will happen. It can also happen if your frequency is reduced. So if you're trying to synchronize the generator at low frequency, the transformer core might get overexcited. So what is the problem with overexcitation when it comes to differential? So as I said, overexcitation is nothing but excessive V over hertz. So if it's excessive V over frequency, there would be increased magnetic flux density. And if the magnetic flux density increases, basically the transformer core is getting saturated. Now, if the transformer core gets saturated, only the magnetizing component or the magnetizing circuit of the transformer will see that current. So there would be high inrush current coming into the transformer primary, but that current would not be reflected on the secondary side. So the CT on the primary would see that high current, but the CT on the secondary would not see that current. Again, there is a difference in currents which the relay will see and which can create a differential to operate. Now, why don't we want differential to operate for over-excitation conditions is the question that should come into your minds. As I mentioned earlier, I'm trying to design a very dependable and secure differential scheme. Over-excitation is not an internal fault, first point. I would not like to have my differential scheme operating on an over-excitation condition because I only want the differential to operate for internal faults. Over-excitation is not an internal fault. The second reason of why we need to have a separate over-excitation protection scheme is if differential is operating for over-excitation condition, then it will be an instant operation. It will instantly operate the relay and the relay will open the breakers. So the transformer will go out of service. But this over-excitation condition can be addressed by automatic voltage regulators and capacitor bands. So these components or these devices can correct the voltage and can bring the system back in the normal conditions. So there has to be different schemes for over-excitation and differential. There is one more property with the condition of over-excitation. After many years of research, it was found that the current which comes in the case of over-excitation is rich in, especially rich in fifth harmonics. So utilizing this concept of fifth harmonic high current, we can restrain the differential relay from operation in cases of over-excitation. So let's see what are some of the methods. So the method one, it says, if my fifth harmonic current goes beyond a certain number compared with the fundamental current, I would declare 87 to block. So that's exactly what we want. We don't want differential to operate for over-excitation conditions. But there is a problem with method one, which has been seen by the people out in the field. The problem is, let's say if you have an over-excitation condition, but during that over-excitation condition, an internal fault happens. According to the logic of method one, differential relay will be restrained. So you have an internal fault, but the differential relay is restrained, which should not happen. So what many relay designers do is they just raise the characteristic in the minimum pickup level in the percentage restraint characteristic whenever they see a fifth harmonic current going beyond a certain value. With this kind of method, security of the relay is intact. And to explain more, when an internal fault happens during an over-excitation conditions, it will just look for this minimum pickup level. And if it's really heavy in value, in magnitude, it might go in the operating region of the relay and can trip the relay. So if you're having an internal fault going beyond the set value, it can trip the differential. And also the over-excitation relay will be operated. So these are some of the methods to address over-excitation. Now the last but not the least is an abnormal condition which is switch on to fault. So what exactly is switch on to fault? We discussed about magnetizing Inrush. When we energize the transformer will experience high current flowing into the primary. But what happens if there is an internal fault during the energization? So if you remember, I discussed about having a restraint during inrush conditions. So when these kind of problems happen, switch on to fault. So when you're switching on to the fault, your differential relay will restrain according to the method we discussed before. So how does a differential relay address that kind of a problem where an internal fault happens during energization? Microprocessor relays employ something called as unrestrained element, and it is usually set above the maximum expected inrush, typically 8 to 12 PU. So if it sees a value higher than this 8 to 12 PU, it says, hey, relay, you don't have to follow any slope characteristic, you just have to trip instantly. So it will trip the relay instantly, even though you have an inrush, but again, it's an internal fault as well. Electromechanical relays, on the other hand, they have instantaneous overcurrent unit in series with the differential unit. So whenever they see an internal fault or any kind of fault which is higher than the inrush current, they just declare the instantaneous unit to operate. So these are some of the abnormal conditions we discussed and some of the challenges we discussed in this webinar. Now to conclude, transformer differential is obviously one of the most popular schemes, but it requires extreme care and attention while setting up. A relay engineer should be aware of all the challenges, all the system abnormal conditions whenever he is trying to design an effective differential scheme. Also, relay engineers should understand how a transformer works and how the CTs are. They should know the characteristics of both the equipment in order to design an effective scheme. And of course, the validation of scheme is crucial for both manufacturers and customers. So once you have designed the differential scheme, it is of utmost importance that you test them. So some of the tests that are being done are commissioning tests, where they test either the whole scheme or just the differential element, and also acceptance tests. And this is where Megger comes into picture. So what has Megger to offer for differentials? So we have SMRT 410, SMRT 46, and SMRT 1 as the equipment for testing relays. It can test any relay out there, especially if we are focusing on the differential relays. SMRT 410 has a total of 10 current channels, a maximum of 10 current channels, and each channel is capable of giving 60 amps. A three-phase differential would require only 6 current channels. So a 46 or a 410 can be used to test a three-phase differential. Smart 1 is our product, is our single-phase relay tester. It has a maximum of 2 currents. So this can test all the electromechanical differential relays out there. And the secondary, again, it can go till 60 amps. For testing your electromechanical differential relay, if you are trying to test a slope, trying to test harmonic restraint, you would require a maximum of 2 current channels. And this has been addressed by the relay tester, which is called a Smart 1. On the top of that, we do have a feature of stacking the harmonics together. What I'm trying to say is only one current channel is needed to do harmonic restraint with any of these three equipment, because we have a feature where we can stack the second harmonic current on the top of the fundamental current in order to test the harmonic restraint feature of the relay. On the software side, we have manual testing features where we can ramp up the amplitude, phase angles the way we want. And we have automated slope tests with slope characteristics of various relays out there in the market, where you can select the slope characteristics and just do it. Just do the slope test. We also have tests for true fault test, where you can, with which you can check the wiring of the differential connections. We also have automated pickup test and some automated harmonic restraint test. With this, I would like to conclude my webinar. If you have any questions, you can contact me on at my email address given here. And if you have any questions regarding the sales, that's the number in front of you. Thank you very much.